Okay, so I just wanted to make a quick video to sort of think about what r squared is. So you could imagine that we're going to be working with this week our scatter plot. So you'll have some x, which will be climate data. You'll have a y, which will be the basal area increment. In this example, I'm just calling them x and y. Hopefully, you could think about what Noel would take points off for this, but I think I've made a good graph this time. And so we saw in the population ecology lab how to add a trend line to this. So you can literally just right click on it, add trend line, and that opens up this window. Remember, we want to make sure it's linear. You could display the equation if you wanted. So here you can see it's like a perfect relationship. And so r squared, we go back into this, we want to get the r squared value. So you can actually just click a button and that's it. Now you know the r squared. And so all you have to know is it's the amount of error that's explained in your data. Right, so these are my observed y's. What I've got hidden here are calculations. So we've got the predicted y, which is exactly the same because there's no error. There's no difference between the observed and the predicted y, and therefore our r squared is 1. We're explaining 100% of the variance in our data. You can see, and that's because all these points are touching. And what I've made is this little tool, which I will make this Excel file available. I've made this sort of error range. So what I'm going to do is when I calculate the, or when I estimate the y's, we're going to just add some error to what we've observed. So right now there's no error, which means we're getting a perfect y. If I change this to 1, you can see it adds a little bit of noise. So our predicted and our observed are no longer the same, and there's some error now. So sometimes they're exactly the same, sometimes they're 1 apart. You can see that just by adding that little bit of error, let's just move this over a little bit. Just by adding that little bit of error, right? So the real relationship we actually knew already was, but you can see some of these points now are no longer right on the line. And our r squared value has gone down a little bit. Still very good. We're explaining like 99% of the variance because these points are still very close. If I change this to 2, you'll see that r squared goes a little bit lower. And you can see that now sometimes we're 1 or 0 or 2 apart, right? So this is 2, the observed value is different. And so, yeah, we can start adding, so let's put this up to 10, right? So now what you can see is the points are sometimes very far from the line, and our r squared value has gone down to like 60% or 0.6 on average, right? And that's because it's still a pretty good relationship, but some of these points are really far, and we can make them very far, or 100, we can set it to. You can see now, it's very, very far. R squared is practically 0 because the observed values are nowhere near the predicted values. That's all r squared is. You're probably going to see really bad r squared values because there's a lot of things going on in a forest, right? So sometimes students get stressed out. An r squared value of 10 or 15 or 20% is probably good for the climate variables. They're often going to be bad, and that's fine, right? That's because if the r squared value is really low, right? So here, our r squared value is, 0.18. That means that there is maybe a relationship between x and y, but it's not a very good one, right? If we set this to something crazy so that r squared goes almost to 0, well, that's just telling you there's no relationship, right? So if you look at a climate variable in the basal area increment and you don't see a very strong trend either up or down and the r squared value is very low, that's okay. That just tells you that climate variable isn't very important for predicting basal area increment. So I'll give you this file so that you can maybe get a sense of how changing the range of the error changes r squared from a perfect relationship to one that is potentially very, very bad. Here, look at this. We've got down to almost 0.2. And you can play around with that. And every time you enter a new number here, it will change the r squared value. And so don't be alarmed if you get some really low r squared values in the climate correlations this week. And unlike the standard deviation, there's a bunch of different formulas for estimating r squared, and they're a little bit complicated. And since you don't need to know it, all you need to be able to do is, let's see, where did it go? Trendline options. There we go. Inside of here, literally all you need to be able to do is click this button and get the R squared to show up on your graph. So you don't need to know the formula. There's a couple different ways. I'm actually not even sure which way R uses to estimate R squared. But this is a good thing to know, right? Whenever you do a regression like this, you probably would like to know the R squared value. And if it's really small, then it's not useful.